Alright, so I'm going to do a quick little video to introduce projectile motion. So this is our big step into two-dimensional motion, and the most common type of two-dimensional motion you do is projectile motion. So this is basically anything that's fired up and goes through free fall, but its initial velocity when it's first fired is not just straight up, it's at some other angle. So it doesn't just go straight up and straight down, it goes off at an angle. Now this angle could be 0 because it could be shot off, say, the top of a cliff and it could fall down, or it could be shot from the ground and it would do some sort of project, or even it could be on top of a cliff and shot off at an angle and do something like that. But basically we're going to try and figure out the motion of this kind of thing. How high does it go, how fast is it going when it hits the ground, how long is it in the air. That same sort of standard stuff that we did with just regular free fall motion when stuff was going straight down. Maybe I should draw the ground in here. It's going down and hitting the ground. But that kind of stuff we're going to cross here. So the first thing we need to look at is what is the shape of this? I drew this path, and I tried to draw it pretty similar for all of these. So what is this shape of this path that a projectile will follow? And it turns out that path is, or at least very close to being, it's a parabola. So it's a parabolic motion where this is just an upside down parabola, kind of like what you get when you do like y equals x squared, but instead of x squared it'd be something like negative x squared. It's a parabola shape that would result from this. And then there's a few properties that kind of go along with this when you have a projectile motion. So let's just do one starting straight from the ground. Here we go. Here's our ground, and we're going to take some sort of ball or something, and we're going to fire it up with some initial velocity vi, and we're firing it at some angle theta relative to the horizontal ground here. And so the first things you have to do is you have to figure out, well, this has a horizontal component to its velocity and it has a vertical component to its velocity, and these two things add up, give us the actual vi. So this one here, just like doing before when we did all these components of vectors, this would be vi sine theta, and this horizontal velocity would be vi cosine theta. So this you could label as v sub y, so velocity in the y direction, and this is velocity in the x direction. Okay, and so one of the big neat things about this is that these two velocities, they're independent from each other. So this vertical velocity is independent from this horizontal velocity. They're linearly independent. The x direction and the y direction, they're orthogonal, they're at right angles, so they don't affect each other. So the basic idea behind this is to break this into two problems. We can break this vector into components, and we have a vertical velocity and we have a horizontal velocity, and from there we can just treat them separately. So what you would want to do with this problem is you'd want to break it into two different problems, a vertical problem and a horizontal problem. And then you're going to want to solve them separately. There's one thing that links them together, but basically you're going to have an initial velocity, a final velocity, an acceleration, a displacement. Vertically we'll use y, and then a time. And then over here you'll have an initial velocity, a final velocity, an acceleration, a horizontal displacement, so an x this time, and then a time. And the thing that links them together is this time here. So whatever this time is here and there, these things are the same. Okay, these two times, they're the same. That's the big link between the horizontal and vertical problem, because however long this has to fly up and back down, the amount of time it spins in the air, well, that's the amount of time, well, one, it has to move vertically, and it's also the amount of time that it has to move horizontally. So no matter what, these two times, they're going to be the same and they're going to be the length. So what you'll want to do is fill out what are all these values. What is the initial vertical velocity? I could even put a little sub y with it, initial in the y direction, final in the y direction, and then initial in the x direction, and final in the x direction. You basically want to fill all these out, and then you'll look and see, and what will happen if the problem is fully determined is you'll be able to solve one of them. You'll either be able to solve the horizontal problem and find the horizontal time, which will then allow you to fill in the vertical time, and then you'll know 3 of the 5 for the vertical and you can solve it. Or you have 3 to the 5 for the vertical, you can find the time for vertical, and then you can come over here and solve the horizontal based on it. But you usually can only solve one, and then once you solve that one, you have to go back and solve the other one. So you got to remember that those times are the big link. Now as this flies up, it's going to follow that parabolic path I was just talking about, and it's going to move just like this over here, and then certain things are going to happen. As it goes up higher in the air, the velocity is going to decrease on it, and it's going to change what angle it's at. It'll stay tangent to this parabola, but this velocity will start to shorten. It won't be as long as it was here right when it started. And then what will happen with the horizontal velocity is it turns out horizontally nothing happens. There's no acceleration. So over here, this acceleration, this equals 0. There's no acceleration horizontally if we can ignore wind resistance, that is, or if it's negligible. And so this horizontal velocity, it just stays that VI cosine theta, where it was this original VI and original theta. So it just stays that Vx. It doesn't change. So Vix, this initial velocity in x, is going to be equal to the velocity for x in every single position, which means Vix equals Vfx. There's no acceleration, and we can just call this Vx, whatever it happens to equal. So at every point I wanted to look at along here, at the very top, I could come up here and look, and I can just go ahead and write this in. This is just Vx. If I'm looking at it right here, it's still just Vx. And if I go down to the very bottom, when I get here, when it's just hitting the ground, this is still just that same Vx. There's no horizontal acceleration, so it stays the same the whole time. Now vertically, there is an acceleration. There is the acceleration due to gravity. So this acceleration vertically is going to be equal to g, that wonderful negative 9.8 meters per second squared, and that's not going to change because basically this is totally independent, and so it just acts like this. In other words, the amount of time this would spin in the air, this whole vertical problem of it, would be exactly the same as if we just fired something up vertically, not perfectly vertically at VI, but perfectly vertically at VY. So we can just pretend it's a totally separate problem, and as it goes up, that velocity gets shorter, and then when it shrinks and shrinks, and then when it reaches its highest point, this Vy is 0. Not Vx, Vy is 0. If you remember from the perfectly vertical problems, at its highest point, the velocity became 0. So it's similar to that here, it's just that at its highest point, only the vertical velocity is 0, not both of them, because this horizontal doesn't change. And then as it goes back down, it'll start getting longer and longer again until it gets back to, if it's at the same height as it was before, this would then go back to being whatever it was, but that would be basically V final in Y, whatever value it happened to be, depending on, how high it was compared to this guy. Is it lower than the initial starting position, or is it up higher, or wherever it is? But it would change based on that, and so we could draw in then what the actual velocity was at each and every little point here as it went through and added it up. And so your main goal is to start with whatever information they give you and fill this chart out and fill this chart out, and then go through and just try and solve whichever side you can. And then once you finish completely solving one side, whichever side you happen to have 3 out of the 5 in, then you take that time and you put it over here and you solve the other side. Now you may be looking at this saying, wait a second, if acceleration is 0, why did I bother writing it down? And if Vix and Vfy are the same, why did I separate them? Yes, technically you can just write 3 unknowns, which would be Vx delta x and t, and that's sufficient for a problem that we would have like we'd had before, where there was no acceleration. So all you'd had was a velocity that stayed the same the whole time, a displacement, and an amount of time. That's true. Uh, but if you think of it the way that I wrote with 5 knowns and unknowns, then you can just always do that same thing. You don't have to learn 3 unknowns for constant velocity and then 5 unknowns for acceleration. You can just do it this way, and then if acceleration is 0, then it'll automatically drop down for you to being down to a 3 variable problem over here, and you have to know 2 out of the 3 in order to solve it. So perhaps they only told you Vx, and you didn't know delta x and delta t, so you'd have to come over here and you'd have to solve this whole side out, because they'd give you this, they would tell you, say, how high it went or something, but they give you the 3 out of the 5 here, you solve it, you move over here. Okay, so again, to sum up the main things, it's a parabolic type motion. It's approximately parabolic. I'll talk later about how it isn't exactly parabolic, but it's so close to parabolic we really can't tell the difference. It's so parabolic, and then you have this separation of the vertical and horizontal components, and as you go through, the vertical velocity changes just like a regular old vertical problem would do, and then horizontally nothing changes. It just moves at a constant horizontal velocity, just like this would do. And so you would solve this just like a regular old horizontal no acceleration problem. That is, I think, about all that I had to say for an introduction to projectile motion.